So my name is Srini, and I do have my colleague who couldn't visit today, but she lives in Zurich, Sudeepa, and we are part of this company called Asfigo. And this is the primary repo that I'm going to be referring to today, in which I'm going to show you how we develop an open source system Verilog test bench linter that you could write your own rules using Python on top of an existing parser, right? And all that code that I'm going to show you today, it's all over there in this particular GitHub, and of course it's open source. So with that, let's get started. So it's a great presentation by Greg and by Dr. Marno, and luckily it's a good thing that, as she said, we could leverage on it, and he was very candid in highlighting the two big challenges. One is the availability of EDA tools to produce chips, both high-end and low-end. FPGA is probably okay because you do get some free tools, if not open source. But when it comes to ASICs, today the state of art is in the top level, like the like your OpenTate, the Earl Grey or Sonata. I don't think we are there yet. Probably 5 years from now, unfortunately. But for let's not lose hope. For smaller chips, especially at a larger, let's say, your geometry such as 180, 90 nanometers, today there are open source platforms available, thanks largely to DARPA and other similar initiatives from across the world, primarily this thing called CHIPS Act. A lot of you probably know about this. So the CHIPS Act has invested quite a bit in terms of doing open source EDA tooling. And they came up with something called Open Road. So Open Road is a specific RTL to GDS2 platform. I have no kind of formal connection or technical connection to it because I'm not a backend guy. But I do mention that towards the end of my slide deck. But that's what the DARPA invested heavily in. And they have built it over a period of time. And just this morning, I saw on LinkedIn, there is new Google Summer of Code 2024 open for those academicians who are interested in contributing and getting a GSOC certificate. And that's on top of Open Road again. So there's a lot of development going on in making things open source more and more. And that's a good thing. And the fundamental problem we're trying to solve here is to design a system on chip today. It could cost from $1 million to $100 million, again, numbers, right? Depending on the complexity, the technology, etc. And there are sophisticated languages, such as I kind of included Verilog into System Verilog because having been in this domain for a while, System Verilog is a superset or superset of Verilog. So we have System Verilog and VHDL. And we have large teams across, and there are major contributors for the CAS are the tool CAS, the team CAS, and the IPs. And I'm glad Low Risk has taken the initiative to make a lot of good IPs available, as well as some amount of, let's say, the costing and all the entire infrastructure, called the DV SIM, for example. It's a beautiful thing from the Low Risk guys to have put together. And I happen to work with some of them in the US to say, okay, what is needed to make it even more easier. And I'm glad it now runs very later, etc. Now, this is one big cost that DARPA identified, and that's why they started investing in the whole thing. The other thing that Greg mentioned was about the availability of engineers. I'm going to talk about that in the modern term of workforce development a little later. So good thing is open source can help us in this case, right? So open source to the rescue. Why open source? Because it is scalable. And I've taken the initiative from the OpenUK team to say that, can you address the sustainability and eco-centric aspects of the whole thing? I do have a slide on it. I will talk a little bit more about scalability there as well. It's easy to adapt. You no longer have these three major EDA tool vendors. I have nothing against it. One of them used to be my previous employer as well. So we all love them. However, you no longer are tied to this not all you can eat deal anymore, right? And it's not like you stick to one EDA vendor and you're done forever. Rather, with open source, you can build as you go. And that's how we mention as we go as a company, by the way. So we want to build it as we go along, right? So we build missing pieces in-house. That's exactly what I did in this presentation. I'm going to talk about the open source linting, because specifically when it comes to test bench linting, specifically the formal, the assertions, the UVM, emulation, there's a whole lot that is missing in the traditional linting, even in commercial tools. So those pieces is what we have built in-house, and we started contributing back. So, okay, so on the CI/CD flow that Greg mentioned, etc., it's all very doable today because you no longer have an additional cost of every check-in is going to consume an EDA tool license. No longer the case, because now you can run a variator check or a PySlint check or variable check, things like that. And you also have a potentially vast and diversified skill workforce. That's another slide that I do have in terms of the kind of team that we were able to gather, not even just employees, but across the globe. So, starting with the technical aspects, I have like few slides on the technical and then go back to the overall big picture. Why do we want lint test benches? The concept in linting is to find bugs early. And I do believe software domain uses this quite a bit. There's something called a PyLint, which is quite popular apparently for Python. So we built it on top of it on similar naming called PySlint, which is for system Verilog Python linting. So you do a shift left, save time and costs. And that's a graph that many of you are familiar with. So what are the specific opportunities in verification, which is what I primarily focus on? I don't do a lot of RTL design. I do some of it, but my primary focus is on verification. So we do have opportunities to lint your system Verilog test benches. The big thing about UVM test benches, because the concept of UVM, if some of you are not initiated with it, it's called Universal Verification Methodology, and it's a big standard. Today it's an IEEE standard. It started with an organization called Accelera, and then it moved into an IEEE standard. And as it goes with many standards, it evolves over a period of time. And there are more than one ways of getting the same thing done in UVM. And that brings a problem to the open source community, specifically when it's vast and diverse. You cannot integrate multiple of these VIPs or verification IPs together, even though they are written with UVM. That's something you could avoid by checking with linting. Similarly, assertions. Assertions is a big topic. I have personally written several books on this topic. So system Verilog assertions is a complex and very nice feature, and that could benefit a lot from linting. We also have acceleration and emulation linting, which we are starting to work on now, and we have formal verification lint as well. These are the opportunities, and I'm going to go a little fast in this slide because it's a bit crowded, and I do hope that these slides will be available for you to download, so you should be able to read it. But very high level, the test bench linting is a new paradigm, because if you Google it today, there are probably 1 or 1.5 EDA vendors making a commercial product out of it. There's no real big-time system Verilog test bench linter, honestly. So why do we do it in open source? It's a new paradigm, but it's a proven concept. If you talk to any RTL engineer, they've been running RTL lint for last a decade, if not more. So the code analysis approaches are changing. Now, there are open source parsers available. So some of it, Greg also mentioned, Variable is from Google. It's a C++-based parser. PySlang, or a Python-based, SLang stands for System Verilog Language and Parser and Compiler. And we built on top of this, and we call it PySlint. So the idea is we don't want to sell you a tool. We want to rather enable you to build your own linters with some case studies that we would give you. So again, the code itself is not interesting. As I mentioned, you can download it and read it for yourself. But conceptually, what we are doing is we are building on top of PySlang, which is an open source system Verilog parser, not done by me, by other people. It's there on the web. You could do a pip install today, and it works. And what we have done is we have taken that and started adding rules using Python. And our intention is not to sell a tool. Rather, we sell, or rather we demo a minimalistic rules as case studies. And we hope customers can start building it on their own. We would be very happy to provide a SaaS model to build custom linters per project, per team, per company, whatever. So in those cases,
It doesn't have to be open source. Again, I'm not a big time, let's say legal expert to talk about it, but the license, which is MIT license, it allows you to own what you're doing. For example, if you say, I have my own rules, I do not want to make it open source, can I use it? The answer is absolutely yes. That's a good thing. You can customize existing rules. You can also do newer analysis, which I have some examples later. So it's not intended, again, I'm not building an EDA company to sell you tools. Rather, it's an open room for innovation. And we're going to talk about qualitative and quantitative metrics. So that's fundamentally what PySlint stands today at. So there are two big parts. One is qualitative analysis, which is typically what you're expecting from a lint. Do you have styles? Do you follow, let's say your packages shall have underscore PKG as your suffix. Your classes shall have a prefix, and so on and so forth. There are specific functional rules. I'll give you some of the screenshots. Again, I'm not going to bore you with the system Verilog language tutorial over here, but rather to show that practically where it can go wrong and how we could use something like PySlint to catch it. There are also UVM-based reusability rules. So these are all many things that we can build. There are some performance rules. There are some simulator compatibility rules, the one that Greg mentioned. Not everything runs in Verilator. Now, let's say you build an APB VIP, and you want to know, would it run on Verilator? Good news is you can actually lint it today to see what changes are needed. I'm not saying all this is available yet, but this is something, this is where we are heading. You could build a rule deck to say that how far away am I from making my code Verilator compatible, even on the test bench side. So you could do that. We could also build quantitative metrics. Two specific examples, assertions and functional coverage. I'll talk about that. So this is kind of a little bit DVCon Europe, which is a month or 2 months old story. So we have about 50 rules today. Again, my intention is not to sell it, but rather to give you and then take it from here. So we have rules across the system Verilog features, and none of it is RTL. That doesn't mean we cannot do RTL rules. In fact, one of our roadmaps is to take low-risk guidelines and implement those RTL guidelines as well on top of PySlint, right? So, but the point is, we want to build something that is missing today, which are your system Verilog constraints, your classes, your coverage, your DPI, assertions, and then general system Verilog. Again, none of this includes RTL lints. So specific 2 or 3 slide examples of what you could catch using it. Again, my intention is not to go through every bit of this particular piece. That's something going to be a detailed system Verilog syntactic stuff. But conceptually, what we are saying is DPI stands for Direct Programming Interface, which allows you to collaborate between C and system Verilog, and vice versa, both sides. So there's something called an import. You could also do an export. When you do that, C is aware of 2 states, whereas system Verilog and VHDL, we have multi-valued system. We have X and Z's in hardware, right? Now, when you use DPI, one good recommendation is not to use the 4 states. Stick to 2-state variables across the boundary. Now, what I highlighted here is a very subtle bug that's going to cost you probably a couple of hours to debug. PySlinted, you would find it in a minute or less, right? So what it is trying to say is output data by default becomes what is called a logic data type in system Verilog, and hence it's compiling code, everything is fine, but at runtime, you're going to find that you're getting a Z on the system Verilog side, whereas the C side looks good. So whereas PySlint would come and tell you, hey, here is what you saw problem. So this is another very recent one. Some of you probably know this gentleman. His name is Avidan Efodi. He works for Apple today, I think. He's in Israel. And he's very nice in putting up a lot of these, or he spent a couple of hours in debugging this tiny example, literally this example. And he says, I spent 2 hours, right, in debugging this. Now, you could argue that you are probably smarter, you could do faster, but probably I'm not, right? So many people are probably not that. It's not going to be all the time you're going to look for this issue. It's something that's going to bite you, and you're going to debug and come back and then start fixing things. Now imagine such a subtle code is costing you a couple of hours. How could we improve, right? That's exactly what we did. Again, as soon as he posted it, we liked it. We kind of took it as a good initiative. Few hours later, we now have a role, right? That could go and catch it. For those who are interested, it is to do with the operator precedence. So you see that there is a double equals and a question or your ternary operator. Between these two, there is an operator precedence that plays, and hence this code wouldn't do what you wanted, right? It should generate between 5 and 6, but it would generate, for example, this large number. So if you want to run it, please go and take a look at the repo. You should be able to see it. Moving on, we could also do, these are the so-called qualitative metrics. We could do more than this. There are a lot of UVM rules. If there are specific interests, I'll be very happy to show you. It's literally running on literally any laptop. You could run it on Windows, Linux, Mac OS, anything. Now, switching gears, we are also introducing quantitative analysis of system Verilog test benches. So what is quantitative analysis? Given a UVC, we call it a UVC. If you want to call it a VIP or a verification IP, that's fine. Let's say you have a PCIe or a UART or an USB, and let's say those are the 3 or 4. Let's say there is an SPI, there's an UART, there is a PCIe, there's a USB, there's a PCIe. Let's just say that. These are the 4 bars that you see. There are 4 VIPs that we ran PySlint on. Now, it can come and give you a quantitative analysis of your test bench complexity. So, for instance, this one talks about constraints. Your system Verilog constraints, how many constraints exist within this particular VIP. The next one, the one in the middle, is showing you the assertions, or the generally it's called assertion, but there is assumption, there is cover, there is also assert, right? So there is a sequence, property, assert, assume, and cover. That's your stats here. The last one here is the functional coverage analysis. Now you got your constraints here, your coverage model, this is how it looks for the same IPs. Now, you could do a lot of interesting analysis. Given this to a manager could go and say, why does this particular IP have so many items and this many crosses? Compare it to another IP wherein probably the number of items is so, number of crosses is less. It's probably okay, probably not okay, right? That's something a manager could quickly get an analysis. And remember, all this is open source and Python. So you could run your own queries to do what you want to do, right? And this is just the start of machine learning and AI on top of all what we can do with UVM test benches, right? Similarly, your IT guy can come and analyze to solve something of this complexity. A low-end tool and low-end machine wouldn't cut it. So you would probably need to allocate a larger machine with large memory and runtime capabilities for this particular IP. In the past, we used to do all this as a trial and error, as an iterative process. Today with PySlint, you could actually run these analysis on top and then make some informed decisions. And again, please remember, we are working with an API which fundamentally is as strong as it can get, meaning it is not your typical pattern matching, like your find, grep, set, and awk. It's a lot more than that. It's literally a language model on which we query, and then we start reporting. Quickly on the assertion part, what does this tell us? This one tells us that the various bars represent the sequence, the properties. That's nice. Number of asserts is here. Number of assumes is here. Number of covers is here. So what does this tell us? This tells us this particular checker IP, I call it checker IP, you could call it AIP or an assertion IP, right? So let's say a protocol IP, written in a system Verilog assertion, this is actually a formal friendly system Verilog assertion IP. Why do I say that? We do not have just asserts. We have, in fact, larger number of assumes which act like constraints in your formal verification, be it Jasper, Yosis, or any other tool that you run. So you could actually now say that this particular IP is ready for formal verification. Vis-a-vis, let's say an IP that has only asserts, you would want to double check, do you really want to run formal because it doesn't have any constraints? You're going to spend a lot of time writing the constraint model, whereas something like this tells you that it is actually ready. And again, it's an analysis tool. You can do what you want with it. These are specific applications that I have come across and my customers are asking to build. So, as I mentioned, just a couple of slides on what we could, I could tweak based on the feedback from the great team at OpenUK behind the State of OpenCon. One of the things that I read is, can you show us how does it, look at the sustainability and how does open source contribute to it? Now, this is the one I was talking about, Open Road Initiative, which is, I haven't done anything with it, but I'm just bringing it to you saying it's already done, which means today you could take your system and run it through this open road. If you have an RTL, you could actually send it off and then get a GDS2 back. And you could send it to, there's also a tiny tape-out program for those who are unfamiliar with it. For, let's say, the hobbyists and the academicians, you could actually start taping out your chip for free or very little cost, about $100 or something, right? Now, this is the one that we developed, PySlint, and the validator is something that I'm happy that they're using it. So you could actually now do a lot of free and open source, and it's faster than any IDE, and it's truly lightweight. It could run on literally any laptop. You do not need a big infrastructure to start running System Verilog and UVM simulations today. And if you wanted an example of an industry protocol, such as the APB or AMBA peripheral bus, we have open sourced this UVC that is compatible with Validator, just to show you that today, UVM plus Validator runs for free. It's a little bit heavy on compile time. That will hopefully improve as we go along, and that's going to happen. Similarly, we also open sourced an assertion IP for APB that's also available here. Now, what is it about sustainability? So sitting in UK or US and a few other countries, probably you don't always think about it. For example, there are many countries across the globe. There are very few internet accesses. Where the country I come from, India, as well as Africa and other places, right? It's not that everybody is hooked up to internet all the time. So trying to sell them, saying, I will give you a free cloud EDA tool for free, which is something that is being done successfully here, right, for a while. But that doesn't cut it for workforce development. Specifically for workforce development, when there are universities spread all across the globe, and every engineer wants to contribute, he or she does not have access to a fast internet to go and do the cloud-based thing all the time. Right? Hence, you need all these validators, the PySlints, the open roads, to try and do it at their end, on their own mission. Right? They can download it and do it at their own. Right? That's one. The other problem with the cloud is, of course, a lot of us know this. The carbon footprint is going to be quite high. Right? Again, I'm not arguing against cloud. All I'm saying is, for workforce development case, I strongly believe cloud is not the answer. Rather, the answer would be really, I wouldn't even call it on-prem, but really the edge-based devices. In fact, take it to even the level that your mobile phones actually can start running simulations sooner than later. So this is where we are, and I wanted to include this. I had a chat with Dr. Morno last evening, and I was happy that he was also looking at low risk, very heavily, and Greg is also here. So we took, and they have published a very nice coding guideline document on the GitHub. So we're taking that and then building it as a rule checker in using PySlint. UVM lint is another thing that we are working on. SVA lint, as I mentioned. Emulation lint is something that we're just putting together so that your test benches can design. You can actually analyze what does it take to do Palladium compatible your gate level netlist. Right? There's a gentleman named Sathapan who is going to help us with all this. I do have his contributor photo coming up. There's also formal lint, which people are leading now. I'm personally interested in doing this more and more right now. It's for automotive, wherein probably some of you already know this. There is an organization called Mitre. It's also an open source common weakness analysis or enumerations here, right? The CWE, that actually gives us lint rules for safety. That's something we are kind of building as we go along. So that's, again, a clue from the OpenUK team was attribute your whatever the contributions have been done, and I'm very happy to have contributions from all across the globe. So thank you, and that's my name and my email address, and here is our repo in case you want to reach us, and we'll be happy to talk. Thank you.